Okay, so okay, all right. So that should be it. Okay, so we've got this worksheet on projections, all those things. Well, the 3.5 one. Oh no, the endomorphism reduction. Is that it? Yeah, this one. And then, well, I think we can do this one quite quickly, and then you can ask questions about the previous ones. Okay? So, first exercise, we've got a vector space E, and we've got a direct sum with two subspaces F and G, and we have some projection on F along G. What are the eigenvalues of a projection? Okay, that's a general result. So that's something we can do very quickly, actually. Right, so we've got like this E is equal to direct sum of F plus G, and we have a projection P such that it's the projection on F along G. Okay, so projections, you can always picture, for instance, what can happen in dimension 2, that's the easiest. You've got one direction, you've got one second direction. You know that the span of the two directions is going to give you R2 because you've got two linearly independent vectors, so that makes a basis of R2. So you have a direct sum. Okay, so that would be your space F, that would be your space G in R2. You really have a direct sum. And the projection tells you that whatever item in that space, right? So let's say that point, right? As you can find an adaptive basis to the spaces F and G, right? But even if I don't talk about adaptive basis, you know that if I've got two vectors here, non-collinear, they make a basis. We've already said that. That's the reason why we have a direct sum. So I can decompose M as one element that belongs to F, the direction F, and one element that belongs to the direction G. Okay, so that would be the unique decomposition of M along F and G, or let's keep maybe the notations X, X1, and X2, right? Like we did, right? And the projection tells you, well, we keep only the X1 part. Okay? So if we've got X, because we have a direct sum, it can be uniquely written as the sum of what belongs to the space F and what belongs to the space G. The projection on F along G of X is we keep X1 and then no X2. Okay? So you can always picture this kind of situation when we talk about projections. If we are in higher dimension, it's really the same kind of thing that is happening. Higher dimension, we've got two spaces. The sum of the two spaces make a unique decomposition in your bigger space. So you will have this. This decomposition is unique. And then you just keep the part that belongs to the F set. Okay, so knowing this, what are the eigenvalues? So let's go back to the definition. Right, an eigenvalue never comes alone, it comes with an eigenvector. And so we must have lambda eigenvalue, V eigenvector. Okay, and so it satisfies the fact that the property that P of V is equal to lambda V. Okay, that's definition. Whatever the kind of map you have, as long as it's linear, it has an eigenvalue. You can find a non-zero eigenvector such that P of V is equal to lambda V. So the two go together, right? When we are in finite dimension and we have a matrix representation, you can find first the eigenvalues and then the eigenvector, but that's the first definition you have to keep, right? So what are the items that would be written like this that will satisfy this property?
Maybe a U from F.
Yes? Yeah, sure. If X belongs to F, yeah? Okay, it means that X is just it's X one part. Okay, so that the projection of X is going to be itself. Okay, so what is the eigenvalue that we have? X1? It's 1, yeah. Right? Eigenvector, anything that belongs to F, eigenvalue is going to be eigenvalue 1. Okay? Okay, because P of X is 1 times X. It doesn't have any X2 parts, so its image is just the X1 and it's itself. Okay, eigenvalue 1, and the question is not about eigenvectors, but eigenvectors, anything that belongs to F, so we can keep as eigenvectors any basis of F, if we can find a basis. Yeah?
I did not understand why P of X is equal to X.
Okay. This decomposition, you have it always. But if X belongs to F already, it doesn't have any X2 part. Okay, so X2 is equal to 0 for any item in F itself. Okay, so when we do the projection, it's just going to be equal to its X1 part, which is itself. Okay? Okay, yeah, sure. Anything that belongs to that direction is going to stay where it is, because its unique decomposition is itself plus 0. Okay? The X2 part is really something like the projection on G in the direction of F. Okay, you've got the other way around. Okay, so we've got eigenvalue 1. What else do we have? So, we saw that for anything that belonged to that direction, it was eigenvalue 1 and corresponds to itself. What's left? What's the other thing we can look at? The other one? Yeah? Okay, so we considered X in F. We found that it did correspond to eigenvalue. Let's consider now some X that is in G. Okay, so in that case, that decomposition, well, this decomposition is true for every item. This time, which one is new? The X1, okay? So the projection of that X, what is it going to be? No. When we do the projection, we keep the X1 part. You have no X1 part. It's what? It's equal to 0. So it's just
X2.
No. That's the goal of the projection is to get rid of the X2 component. Yeah, 0. The 0 element, okay? It's the 0. Because it doesn't, well, its x1 part is 0, so its projection on F is just 0. Anything that belongs to this direction is going to be projected to this single point. Okay? That's what we're doing. So how can we interpret this in terms of eigenvalues? Come on. We've got one eigenvalue here that is appearing. 0. Okay? 0 is an eigenvalue. It's a possible value of 4 eigenvalues. Anything, any real value, if you work in real, any complex values, if you work in complex, can be an eigenvalue. So 0 belongs, so the real number 0 belongs to the spectrum. That's another way to say that. 0 is an eigenvalue of P, it means it belongs to the spectrum. That's just equivalent. Spectrum is the set of all eigenvalues. So that's one way to say that some value is an eigenvalue. So we had one. Okay, so actually we can say that even the spectrum of P is equal to 0, 1. Well, we should prove that we can't have any other value. Well, how could we say? We could say that, well, if we've got an eigenvalue, P of x is equal to lambda x and should be equal to x is, if I use the same decomposition, lambda x1 plus x2, and so, and I know that the x2 part should be equal to 0, so that should be lambda x1. Okay, so we obtain that if we've got non-zero eigenvalue, P of x is equal to lambda x1, and could we have anything different? Oh yeah, if we've got if we know that the property of eigenvalues is that no, it's not going to. So how can we prove that we can't have any some value that is different from 1? Oh, we just already, we've already proved anyway that it was equal to 1. Oh, no, yes, of course. Right, if we've got an eigenvalue, it satisfies that. But if P of x is written as x1 plus x2, that should be equal to x1 because it's a projection. P of x is equal to x1 because it's a projection. We have this, and on the other side we've got that it should be equal to lambda x1. So either we've got x1 is equal to 0, and then it's all right, and we get the 0 eigenvalue, or we get x1 is different from 0, and then the only possibility is that lambda is equal to 1. So the only possible values are going to be 0 and 1. Okay? Right, so we've got those two properties. This because we assume we've got an eigenvalue. This because we've got, by definition of the, that part by definition of the projection, and so if I've got x1 is equal to lambda x1, it means that lambda is either 0 or lambda is 0 and then x1 is 0, or lambda is equal to. Okay? But, all right, so this is the global reasoning for the eigenvalues, but we could already say that in finite dimensions. Why? Have you looked at the exercises on projections? Or even the lesson? I mean, it's in the lesson. What's about infinite dimension? We've got an adapted basis. So what's the matrix of a projection in the corresponding adapted basis? What does it look like? Let's do it again. Take this example, for instance. So what's the adapted basis? It's the one that corresponds to the concatenation of one basis of F and one basis of G. Okay? And you know that if you take them together, that's going to be a basis of the whole set. That's the idea behind the direct sum. Okay, so you've got a basis of F. Here, if I do in R2, where I just have one vector, okay, let's call it A, stuff. Basis of G, again, in R2, I'm going to have one vector. Right, so if I want to make the matrix of the projection in, so, right, if I make this, if I take the two vectors, that's what it's for, we are making R2. Okay, this is spanning the whole of R2. Is that okay for you, up to that point? Okay, so that's the thing with direct sums. Even if I've got more vectors in each, if I've got more dimensions, the idea is that if I take a basis of the first one and after it's a basis of the second one, I've got a basis of my whole space. So here I'm going to have R2. If I want to make the matrix of my projection in that adapted basis, you know that I have to write in columns the images of my vectors. Okay, expressed in that basis, right? What is P of A? A is the direction of F. So P of A is 1. Okay, it's 1 times A. Tip so. Okay, A is one vector of that space. Right? So it's 1 times A and 0. P of B. 0. Okay? So it's 0 and 0. So that's the matrix of the projection in this adapted basis. And here, as it's a diagonal matrix, well, we could show like we did during first semester, as it's a diagonal matrix, it's unique. Okay, so if you would write the diagonalization, while you have the eigenvalues on the diagonal, right? That's already the diagonalization of your matrix. So the eigenvalues, you read them on the diagonal. So that's 1 and 0. Yeah. Okay. Any questions?
If you could quickly explain how you found the values of the matrix, please.
Yes, I take in columns the image of the basis items. Okay, P of A is equal to A. So it's 1 for the row corresponding to A and 0 for the row corresponding to B. P of B is 0. Yes?
Why is P of B 0?
because B is something that belongs to the G space. So if I use the decomposition in as x1, x2, B has no x1 and its x2 is itself. Okay, and similarly, A has no x2, but its x1 is itself, it's A. Okay? Well, the arrow is maybe misleading. It all begins with one thing. Well, when I'm speaking about R2, is that a point and a vector is the same thing. Okay, maybe there's something here. We are always, that's a geometric location of a point, but actually what I'm showing here, it's the vector that goes from 0 to this one. In terms of vector space, we speak about vectors. Okay, so so that's a vector that is composed of the sum of the vector here plus that vector. Yes? Let's see if you have understood. Let's say that I'm in R3. So in R3 I need 3 directions. Let's say I've got a plane and I've got some direction. I'm purposely taking something that is not orthogonal because we will deal with orthogonality next chapter. Okay? So we've got another direction. So we've got, let's say we've got A and B to span my plane. Okay? So that's going to be, let's say, some space F. Right, so I've got a plane, 2 directions, let's call them A and B. And I've got a third direction, let's call that C. Right, and that's going to be the space G. G is equal to the span of C. Okay, I've got a direct sum. Why? Because I know that if I take A, B, and C, they are going to be 3 linearly independent vectors. I'm in a space of R3, so I know that the whole stuff is spanning R3. Okay, so I have that. If I concatenate my 2 bases, so AB is the basis of F, C is the basis of G, I've got R3. Okay, so I know that anything in R3 can be decomposed as some, well, X1 part. Let's call that XF to stress out the fact that it belongs to the space F, plus some XG part. Okay, fine. What do I have in colors? You've got some points. Well, imagine it's in 3D, so you've got your plane, you've got your direction, and you've got some points somewhere in R3. Okay, so you can project along this direction. Okay, you follow, you align parallel to your line. That's going to meet the plane here. Okay, so that would be the XF part. And similarly, you would have something here, the XG part. Okay, and if I say I want to do the projection on F along G of X, I just keep what belongs to the plane. Okay, I will just keep that part. Make 0 for this one. What would be the map of this projection in the adaptive basis? So I have to take P of A, P of B, P of C. Okay, again, expressed in the basis ABC. So that's my adaptive basis. Yeah.
1 0 0 0 1 0 0 0 0.
Yeah. P of A, as it belongs to my plane, is going to be 1 times itself. Okay, there's no reason it should change. It's the unique decomposition of A along AB, right? So 1 0 0. P of B, same thing. So 0, 1, 0. And P of C. C belongs to the direction of the projection. So it's going to, anything that belongs to G is going to be sent to that 0 point. Okay, and I know that it's going to be the 0 point because they are linear space. Okay, it's not just any plane and any line in R3. It's just, as they have to be linear spaces, it must be some plane that contains the 0 and some line that contains the 0. Right? So that's the 0 element, right? And so C, P of C, is 0. Okay? Now, if I want to express that in the standard basis of R3, let's give that some names. Well, IJK. IJK is nice. Well, no, E1, E2, E3, because I don't want to write E1, E2, E3. Standard basis of R3. What should I do in order to get the matrix of this map in the standard basis? That's the thing I wrote the correction of. You have to make a change of basis, right? To go from standard to adapted and apply your transformation in the adapted basis and then go back from adapted to standard. That's the idea. Okay, so you have, let's say that this is your matrix M in the adapted basis B. Let's call that B, this adapted basis. The relation, if you want to write it in the standard basis, you have passage matrix and B, P minus 1. Okay, you go, right? And that's giving you the matrix in the standard basis. I don't know how to call that. C as Cartesian basis. Right? How do you make your matrix P and P minus 1?
Diagonalization?
No. Your matrix B is going to contain something that you directly have. Yeah?
The eigenvectors.
No. That's not really well, in the end it corresponds to the diagonalization. But here, what are the eigenvectors if you want to? Yeah.
All of the E1, E2, and E3.
Well, not them. The A, B, C. Okay?
Yeah,
E1,
A, B,
E2,
C,
E3, the usual standard basis of R3, the IJK, right? And then you've got this adapted basis, right? A, B, and C, well, some that are spanning my plane and my third direction. Okay, so in P, I've got the vectors A, B, and C expressed as we know how to express them in the standard basis. Right? And then P minus 1, you can calculate it. So these are columns. P minus 1, you calculate it out of this one. Right? And that gives you the matrix of your projection in your standard, in the standard basis. What can you do with it? You are given any point in R3 expressed with its usual Cartesian coordinates. If you want its projection on that plane, you just apply the matrix to these coordinates. Okay? What is that for? Then MC is going to represent the projection, the one we are talking about, on F with direction G in Cartesian coordinates. So if you are looking for this, what do? You take some x expressed with Cartesian coordinates, so x, y, z, and you apply this matrix, and that's giving you the projection of your x, y, z. Okay? What's happening here? When we apply this matrix, we apply first p minus 1 to the Cartesian coordinates. First thing is going to be multiplying by p minus 1, which take you from Cartesian coordinates to the coordinates in the adapted basis. That's the change of basis matrix. From Cartesian to adapted. Once you have expressed your x, y, z in the adapted basis, you can apply the nicely adapted projection matrix. Okay? Once you've done this projection, you have to go back to the Cartesian coordinates using matrix P that takes you from adapted to Cartesian. Okay? Right? And I hope not to confuse you more, but we get back to this very important idea, which is when you know the image of some basis, you know everything about a linear map. Okay? Why? Simply because if you have a basis, let's say that A, B, and C is a basis of R3, okay? It means that any x in R3 can be written as some coefficient times vector A plus some coefficient times vector B plus some coefficients times vector C. Okay, I've just expressed the fact that I've got a basis, so it's spanning, so anything can be uniquely written like this. X will have those coordinates in the basis B. Okay? I've written trivial things here. I've said I've got a basis. That means anything can be expressed as linear combination of the basis items. And in that basis, these are going to be the coordinates. Okay? So this is completely trivial as is. Now what's happening when I have a linear map, whether it's P or whatever? If I've got a linear map in general, if I want to compute the image of something that is in my space, well, I'm going to use that decomposition. So that's XA A plus XB plus XCC. So I've just substituted X by its expression in that basis. And now if I use the linearity of the map, that's really a linear combination. So I'm going to have the linear combination of the images. Right? So using the linearity of the map, XA, XB, XC are all numbers. So this is XA f of A plus XB f of B plus XC f of C. Okay, so what do we have in the end? I just have to know the image of the basis items in order to get the image of any item in my space, of any element of my space. Okay? And if ever you write this, you can write this as a matrix equation. That's going to be the matrix that contains the columns f of A, f of B, f of C times AB, XA, XB, XC. Okay, this can be expressed with a matrix in a matrix form. Also. Okay, so we're all it's all completely consistent, of course. It's that's right. Yeah.
By x, y, z on the right,
Yeah.
do you mean that they are the coordinates of any point in
Cartesian.
in Cartesian coordinate? It's not I, j, k, or E1, E2, E3.
So x, y, z are going to be values, real values. I, j, k, or E1, E2, E3 are vectors. Okay, so the coordinates are just the real values. It means that my point is x times E1 plus y times E2 plus z times E3.
Yeah, because E1, E2, E2, E3 to me were already in the MC matrix, so I didn't know why you put X, Y, and Z again.
Ah, here.
Yes,
This is matrix times vector.
but the E1, E2, E3, they are already in the MC.
No, MC is the matrix that I get when I express this one in the Cartesian coordinates. MC is a new matrix. It's the same map as this one, but expressed instead of saying in the adapted basis, I have it in the Cartesian basis.
Okay, so in IJK.
In IJK, yeah. Okay. All right. So yes, so you've got some exercises very typical in the one that I've written the correction of, right? Previous worksheet. I know we didn't really have time to work on it, but it's really simple techniques that get back to that one, right? So either you have some matrix and you want to extract the spaces F and G. Okay, so in that case, well, it gets to looking for the eigenvectors for 1 and the eigenvectors for 0, right? You're looking for something that is going to solve P of x is equal to x, right? That means these are all the items that belong to your space F. So you're looking for the null space of P of x minus P minus identity of n minus identity. Okay. That's one way to say it. Or you're looking for the image. Well, if you look for the null space of this, you get the G space. If you look for the image, which corresponds actually to the kernel of n minus identity, you get the F space. Okay? So either we have some matrix expressed in Cartesian coordinates and we want to find its geometric characteristics, okay, the F and G space. Either we are given the geometric characteristics and we ask you to build the matrix, which is going to be that way. Okay? So the other kind of transformation we have is the symmetry. So the linear symmetry with respect to a space along some direction. So if we keep the same example first, we've got some space F, some space G, you've got some x1 and some x2. Okay, now if the other kind of transformation we've seen yet, do you have questions? Okay, so the other kind of transformation we have seen is the linear symmetry. It begins the same way. We've got two spaces that make a direct sum. Okay, and when we take the symmetry, we keep the x1 and we take the opposite of x2. Okay, that's so the S symmetry of minus x is x1 minus x2. Oh, there's something I had forgotten. One of the properties of the symmetry is that, well, if you take the symmetry of that point, you get back where you started. Okay, so one of the properties of the symmetry is that if you apply it twice, you're back where you started. Okay, if I take the symmetric with respect to that line in that direction of that point, I'm going back where I was. Okay, so in terms of matrix, in terms of matrix, if I've got my matrix S representing my symmetry, it means that S squared is equal to the identity. Yes?
Can you just re-explain the property?
Okay. Projection. So, same example to illustrate. We are in R2 and you've got two directions, non-collinear, so you can make a basis, and you know that any x can be expressed as one thing that belongs to the direction and another one that belongs to this one, right? In the projection, we kept that value on. Now in the symmetry, we want just to take the symmetric of this point, of this vector, with respect to this line in the direction. Okay, so I'm landing here. Right? So that's it. So what does it correspond to? That point has the same x1, but we take the opposite of the x2 component. Right? So the symmetric of x is going to be written as x1 minus the x2. Okay? One simple property we can get is that if we apply again the symmetry, the linear symmetry on that point, we are back where we started. Okay? So that's one of the properties. Well, that's the main characterization of the symmetries, even. And that just means that S squared is equal to the identity if you have a matrix representation. Okay? So, one way to check whether you've got the matrix of a symmetry is to square it, and if you've got identity, it means you have a symmetry. Okay, if you have a symmetry, then you know you can look for its corresponding spaces F and G. Okay? Let me go back just 1 second to the projection, because I forgot to say this. What's happening if you square the projection matrix, which we have called M? Same thing, all right? Let's keep this image in mind. You've got your point, the x1, the x2. You project x on that direction, and so you just keep x1. Apply the projection again. What do you get? x1 again. You don't move, right? So what you get when you apply twice the transformation, which corresponds to squaring the matrix, the same thing as if you just apply it once. Okay? So if you want to characterize, if you've got a matrix and you square it and it's equal to itself, it means you've got a projection. If you've got a matrix, you square it, you've got identity, you've got symmetry. If you square it and you've got nothing of this, you've got nothing of this. Okay? So I think one easy exercise, okay, which is very systematic, is I give you a matrix and find out what kind of geometric transformation it relates to. Is that a symmetry or projection? So you just square the matrix, see whether you have M or identity. Once you have identified it, you find the F and G space. Okay, either using the eigenvalues 1 and 0 for the projection, or the kernel corresponding to eigenvalue 0, and the image that will correspond to the eigenvalue 1. Right? And for the symmetry, well, let's look for it. Right? What are the eigenvalues that we're going to have? Yeah. Sure. So how do you prove it? So again, we've got two spaces, so when you don't really know what to do, you just use what you have. What we have is that we've got those two spaces. So let's see what's happening. If I take X that only has some X1 component, right? So something that belongs to that set. If I apply the symmetry, we're staying there. Okay? So what do we have? S of X is equal to itself. Okay, because it only has S of X is X1 minus X2, but X2 is 0. Okay? So we've got eigenvalue 1, and it corresponds to eigenspace anything that belongs to my linear space F. Okay, so eigenvalue 1. And let's try the other possibility. If we've got something that is going to be in G only, so x1 is equal to 0, what do we get? So if I've got something that belongs only to that direction, what is the effect of the symmetry for this one? Yeah, we get sense on the other side. Okay, so S of x is minus x2, so minus x. So in terms of eigenvalue, -1. Okay? Okay. Let's write the matrix of the symmetry. So maybe we can, matrix of this in, so let's say you've got one adaptive basis, which is A and B. Okay, so it spans R2, because I've got two linearly independent vectors. So what's the matrix of my symmetry? So what do I get on the first column? S of A. 1, 0, yeah, it's itself. S of B. Yeah. Okay? So in the adaptive basis, this is the matrix that I get, and if I want to get it in a Cartesian basis, I have to use again the same formula for change of basis. Okay, so if I want, so that's my matrix in the adaptive basis, in the Cartesian basis, I will have P and P minus 1, with the P being the vectors A and B in the column. And P minus 1 you can compute. Okay, and if you are looking for, if you are given a matrix and you're looking for the corresponding sets, spaces F and G, you have to look for eigenspaces for eigenvalue 1 and eigenvalue -1. Okay? F is going to correspond to, well, it corresponds to the eigenvalue 1, so that's going to be the kernel of M minus identity. Okay, that's eigenvalue 1. Well, that's going to be eigenspace for 1. And G is going to be the eigenspace for -1, right? So that's mx is equal to minus x, so that's m plus identity. So that's the kernel of m plus identity. Eigenspace for -1. Okay. What are the questions in that? Okay. So that was for symmetry in finite dimensions. The next question tells you that, well, we can make symmetries even if we don't have any idea of the dimension of our spaces or if it's infinite dimension. Okay, so second question in that exercise 2. All right, so everything we do here includes everything what was on the previous worksheet. So don't worry, because if we haven't really worked on the previous worksheet during class, because this is exactly what's inside of it. Okay. So I'm still in exercise 2, but now I'm considering a space of real functions on R. So that's infinite dimensional. Okay. So that F is an endomorphism. So we've got some map that goes from F of R to something. And, well, it said that if you take a function, you get another function. And it's the function if your input is a function that is called F. And for X gives you F of X. Your output is going to be the function that for X implies F of minus X. Okay? I think my notations weren't very good. Okay, so that it's an endomorphism. Endomorphism just means we've got a linear map from one space to itself. Okay? So two things in that definition, from one space to itself and linear. Okay? So the from one space to itself is usually quite easy to show. We've got a function, we get a function. Fine. Right? That obviously is something that belongs to the set of real functions. So what we need to show is the linearity. Linearity means if I take, as usual, I take two items in my space, so F1, F2 that belong to my space of functions, so two functions. And a real number. Do I have that the image of the linear combination is the linear combination of the image? So we have to compute S of lambda 1 plus F2. Okay, so according to the definition of my map, my input is going to be the map that for X I apply lambda F1 plus F2 applied to X. Okay, that's my input. Output of this, the map where I apply this to negative X. Okay, that here I've just applied the definition of my map. Okay, but it happens that this map, the one that for X gives you lambda F1 plus F2 applied to negative X, well, even this we can clearly see that the sum of two functions applied to value is really the same thing as the sum of the two functions. Okay, I'm taking sum of functions applied to some value. It's the same thing as the sum of the values of both functions. Right? Okay, so if I do that, that's going to be the map that gives you lambda F1 minus X plus F2 minus X. Right, so this, right, that's equivalent to the map that for this gives you that. Okay, and this is really the sum of the map that for X gives you lambda F1 of minus X plus, or I can even say that it's lambda times the map that for X gives you F of minus X plus F, the map that for X gives you F2 of minus X. Okay? So in the end, I really have that this is lambda times the map for F1, the S of F1, plus the S of F2, okay, which we should write. Okay. So yeah, so it's linear. Okay, the image of linear combination of the map is going to be the linear combination of the images, right? So we've got indeed an endomorphism of that set. I remind you that we can write it belongs to L of my set of linear maps from this set to itself. Okay, so that's just a very convenient notation. So if the question comes after the first one, it means there must be a relation. Okay, so how could we check whether we've got a projection or a symmetry? Yes? We square it and see what we get. Squaring a map is the same thing as applying it twice. Okay? So this notation, yeah, we really didn't use it a lot for real functions in general, but why is it well adapted to linear maps? Because the typical example of a linear map is a matrix. Squaring a matrix, applying it to a vector is the same thing as applying twice something to a vector. Okay? If your map is represented by some matrix M, the effect of your map on some vector is going to be M times X. If you want to apply again your map on it, compose your map with itself, it's just the same thing as squaring your matrix. Okay, so that's why when we have a linear map, when we have S squared, for instance, it means that we apply twice our map to the same item. Okay, so let's try to square this, right? What does it mean? It means that I want to apply again my map S to this function. May you erase that? So what function do I get if I apply it, starting with this input? I'm going to have some function that for x applies f of minus x. So f of x. Okay, so indeed, I'm back where I started. So we've got a symmetry. Okay, so from this, we can say that S2 of f is equal to f, so S is a symmetry. So linear symmetry. So we know it has eigenvalues -1 and 1. So we can find the corresponding spaces, little spaces. Yes?
So we have to apply twice the map we have here, but can we do it with the matrix or not in this case?
No, we can't have any matrix representation here. How would you make the matrix
I
representation?
don't know, that's why I asked.
Yeah. You can get matrix representation when you've got a basis. That's how we build it. We don't have any basis of that space. Okay? And even if we had, which we don't, and we never will, we have some basis for more restricted spaces than that, it would be infinite dimension. Okay, so when you have no ID, you can't make the map, right? And you have no ID, maybe because you have no idea how to get the basis of your space, or maybe just simply because it's infinite dimension. Okay, so when you don't have a matrix, you have to go back to the original properties, right? So original property, if I square my map, what do I get? If I get that I'm back to where I started, it means that it was a symmetry. Okay, now let's find, so I know according to the first question, I didn't prove it only on the matrices, we proved it in general, okay? Just using the decomposition, that it had eigenvalues +1 and -1. Okay, so we know that the spectrum of F okay, +1 corresponding to the F space, the one we take the symmetry, with respect to which we take the symmetry, and -1, the direction of the symmetry. Okay, so keep, I think it's very useful to keep that ID, all right? So that's the F space corresponding to eigenvalue 1, because if you started there, you stay there, and that's the G space corresponding to eigenvalue -1. Because if you start here, you get same space but opposite value. Right? So if I find the corresponding eigen spaces, that's going to tell me what kind of symmetry I have. Right? So basically, if I'm looking for eigenspace 1, okay, for eigenvalue 1. I know it exists because I've got a linear map and I know it's a symmetry and I know that symmetries have eigenvalues 1 and -1. Okay, so I know that we can find this. So what should I look for? I should look for functions f, right? My space is going to contain functions because we're in a space of functions. Functions f that will satisfy that. Okay, that's the definition of eigenvalue 1. Of something corresponding, eigenvector corresponding to eigenvalue 1. So what are the functions such that if I apply the function to the opposite of the argument, it's the same thing as the function itself? What are the functions such that this function is equal to that function?
No function?
Not the constants, but the functions. The absolute.
So what do I want? So 0 would work. Absolute value would work, but that's a very specific kind. Square function will work. These are examples. What's the property? What is, if you have a function that satisfies this, what does it mean? What kind of function is that? I heard it in French at least. It's an even function, yes. Yeah, it's even. Okay, so the eigenspace corresponding to eigenvalue 1 is the space of even functions. what about the other eigenvalue? What is the going to be the, so that's my F space, the one that won't change if you apply the map. What would be the other one? That's right. Okay, so the other one is going to be corresponding to, so eigenspace -1. It's going to be the one where you've got, so you start with x gives you f of x, f of x. You apply, well, you know that it's going to give you x gives you f of minus x, right? That's when you apply s in general, but for your function that corresponds to eigenvalue -1, what should we get? Minus. Okay, so basically, I'm looking for functions that will satisfy the same thing, right? They are both, well, that would be their image by S, but if it corresponds to eigenvalue -1, that would be also their image by S. Okay, so what are those functions? Odd functions, yeah. Actually, I'm pretty sure this is one exercise you did in year 1 to show that any real function can be described as the sum of an odd function and a real function, and an even function. So you really have a direct sum between even functions and odd functions in order to create any real function. Okay, so that's one typical exercise you probably have done in your. Okay. If not, think about it. If you don't see or ask me, it's a nice one. I think it's a very nice result to see that any function without any kind of parity can be described as the sum of an odd one and an even one. Okay, that gives you the direct sum. Okay, right. Any questions on that? Okay, so let's do the exercise 2. Very typical again. Do you have any questions? So we've got now a map from Rx to Rx, meaning from the set of polynomial functions to the set of polynomial functions. Maybe I can try first to make, let's say, a simpler one. Let's reduce that maybe first to R3 of x, polynomials, and then we will see how we can generalize. Okay? If we got polynomials of degree at most 3. All right. Okay. The question is, no, it's not going to have to go in R3 of x. We have to see about this. I'm going to make the domain R3 of x, and we will have to find what the codomain would be. All right? So we've got our map. We take some polynomial p, and we get another polynomial. That's pretty clear, which is going to be x plus 1 times x plus 3 p prime minus x times 2. Okay? What is the degree of that polynomial? If P has degree 3. 4. Yeah. Okay? If P has degree 3, then if I multiply it by x, I'm going to get to degree 4. Here, if P has degree 3, I've got P prime degree 2. Multiply by some x squared, I'm going to get, so that's also degree 2. I get something degree 4. Okay? So if I want to restrict my map as is, I have something that goes from R3 to R4. Okay? If I want to talk in terms of kernel, or of null space, kernel, and image rank, if I want to apply the rank nullity, what should we have? So, if I've got the rank nullity theorem, would tell you that so here I've got finite dimensional map, right? So what should it be equal to? Yeah. Dimension of which one? The domain. Okay, it should be equal to 4. Dimension of R3 of x, that's 4. Dimension of R4 of x, that's 5. Okay, why? Because you need the constant. Okay, constant x, x1, x2, x3, and 4. Right. Okay, so what else can I get? The rank. Can it be bigger than? Could I have a surjective map? No. Yeah. Okay, because even if the nullity is equal to 0, that means the rank will be at most 4. Okay, and my codomain is of dimension 5. So I know that if this is my codomain, it's not going to be surjective. Okay, is that clear for you? Right. So what are the questions? Show that it's an endomorphism and find its spectrum. So it's not an endomorphism for us because I've restricted that to some finite dimensions. Okay. In the original question, we have R of x, which is just a polynomial. Okay, any polynomial of any degree. So there we could have endomorphism because we go from one polynomial and get one polynomial. Here we take one polynomial of degree 3 and we will get probably something of degree 4. Okay, so it's not going to be an endomorphism, but we can still work on the linearity. Okay, so let's show that it's a linear map from R3x to R4x. So what should I do? Take two polynomials, take a real value, and take the image of a linear combination. Okay, as usual. Right, so that would work for even if I don't have if I haven't done any restriction. Okay, so we want to do f. Okay, so what do we get? We're going to get x plus 1 times x plus 3 times derivative lambda p1 plus p2 minus x times lambda p1 plus p2. Okay, you will see that it's going to be very simple now. Expand, use the linearity of the derivative. and that's it. Okay, and we can write that x plus 1, x plus 2. Derivative of lambda p1 plus p2 is lambda p1 prime plus p2 prime. So I can even write it as lambda p1 prime plus p2 prime. And I've got minus x minus even minus lambda x p1 minus x p2. Okay, and I can really rewrite this as lambda f of p1 plus f of p2. Okay, you always know this is where you start and this is where you end. In the middle, the calculations are usually simple. Okay, so we've got a linear map, and we want to know about its spectrum. So if I have restricted that to this, what could we do to find the spectrum? Yeah.
I don't understand why we go from x plus 3 to x plus 2.
Oh yeah, it's my error. Sorry.
And also I think it's a minus and not a plus.
Where do I have a minus?
It's in the original copy we have a minus on the
Where?
x minus 3.
Oh, it's x minus 3. Okay. Fine. I've got an old version, so.
Okay.
Yeah, correct me if that doesn't correspond to your answer. Yeah.
I don't understand why we restricted the original.
To make it simpler first. Okay, to understand. Right? Why? Because here you're in finite dimension, you can have matrix representation. So anything you work on the matrix will work on the matrix. Now, if I don't restrict that, I mean infinite dimension, I won't have any matrix representation. Okay? All right. But that's going to give us a good idea, anyway, of how this map is working. So, as I've talked about matrix representation, if I'm looking for eigenvalues, I should look for p such that f of p is equal to lambda p, okay, in general. Now, if I'm in finite dimension, the good thing is that I can have this matrix representation. Okay, so let's make it. Okay, matrix representation. So maybe you can do it, or somebody can come and do it on the board. Okay, if I'm not mistaken. I will write it, do your computations, and we will see. Did you get the same thing? Yeah, okay. So, yes, we're just looking for the, the images of the basis items, and this is what we get. Okay, so if we're looking for the eigenvalues of this, what should you do? We should have taken out 2 of x instead of 3 of x. Anyway. What should we do if we were looking for the eigenvalues? We look for the corresponding eigenvalues, eigenvector of this matrix. Okay, I agree this was maybe not the best choice I could have made. Of O3x to restrict it, because we still have something of degree 3. Okay, so how do you look for the eigenvalues of a matrix? You take your matrix minus lambda the identity, you make the determinant and look for the roots. Okay. Okay, that was maybe not the best idea to restrict it to that space. If I restrict it to R2x with image, then in R3, that's going to restrict to this one. Okay, so for this one, it's easier to look for eigenvalues. So eigenvalues, you have to add a zero column, and that's going to make it. So for the eigenvalues, you need a square matrix. So you would need a 0 column to add a 0 column. So that would make it complicated. Well, that would make it complicated. You would have 0 as an eigenvalue. Okay, so all right, that was maybe not a very good simplification, but anyway, that was making the matrix of a map on polynomials. Yeah.
I don't understand how to get the eigenvalues, considering that it's not a square matrix.
That's what I said. That's going to be a problem. You should add a column of 0, and then you are sure to get a 0 eigenvalue. Okay, but. Alright. Yeah, so working on this matrix was not very interesting, apart from the fact that you had to construct the matrix on this one. Okay, on that example, it's not really an endomorphism, it's not going to work. But what's interesting is that you see when we've got degree, degree 0 gives me something of degree 1. Degree 1 gives me something of degree 1. That's interesting. Degree 2 gives me something of degree 3. Degree 3 gives me something of degree 4. Okay? So if I'm just looking at that, what possibilities would you have for eigenvectors? Could you have something that is only a constant? Okay, let's think from this one. All right, that's interesting anyway. If I'm looking for eigenvalues, eigenvectors, I'm looking for things that are going to satisfy f of p is equal to some value times p. Okay, that's definition of eigenvalue, eigenvector. What does it mean? It means that the image has the same degree as your polynomial. If you plot something of degree p, and it corresponds to an eigenvalue, eigenvector, you've got the image that has the same degree. Okay, so we can first exclude pure constants because the image has degree 1 when we plug something of degree 0. We can also exclude anything that is with x2 and with x3. We can exclude anything that is in x2 because the image is going to be degree 3. And if I plug some x3 in order to compensate for this one, I will get some x to the 4. Okay? So what is the only possibility if ever this works? It's when we've got degree 1. Okay? So the only possibility, if that is okay, is that we've got a degree 1 polynomial. Because if I take only constant, that's not working. If I take something of higher degree, I'm going to get something of even higher degree. Okay? Later on, we're going to prove that if we plug something of degree n, okay, we will get something of degree n plus 1. We will prove that afterwards, okay? But just from that, we see that it can't be some x2, it can't be some x3, it can't be 1, so it must be only degree 1 polynomial. Okay? If I combine degree 1 and degree 0, I will get degree 1, degree 1. So that works. If I add anything of higher degree, degree 2, I would get degree 3. If I add some degree 3, I would get some degree 4. Okay? So if that is a valid equation, P must have degree 1. Okay? So if P has degree 1, what should it be written as? It's constant plus a first degree term. Okay? So it means that P should be written as A plus Bx. Okay? So how can I find the A and B now? Yes?
I don't get why the degree 1 is correct. And why it's not just like the.
Why not just?
Why we get 1 degree for f of x?
Yeah.
You get x2.
Here? No, we get the image is minus 2x minus 3. That's the image in the end. Okay? The one I plugged in the in my matrix. Okay? So yeah, if I've got degree 0, I've got degree 1. Image of degree 1 is degree 1. Image of degree 2 is degree 3. Image of something degree 3 is degree 4. And we will get that it goes on. Okay, let's do it now before we look further. Let's show that if you plug something of degree n, you will get something of degree n plus 1. Okay, so if the degree of P is n, that means P will be written like, well, A0 plus A1x, etc., plus ANXN. Okay? Just so I've got the polynomial of degree n. What's going to be the highest degree of the image of P? That's going to be the degree of, well, what I have, f of P, x plus 1, x plus 3 times P prime minus x of P. Okay, that's going. I'm looking for the degree of this polynomial. So what is that going to be? If I take now in general P, degree of P is equal to n. Yeah, but we have to show it. Okay? What's going to be the highest order term in that thing if what I plug in is this polynomial? We have to do it. So here, the highest order term here is going to be minus ANX n plus 1. That's going to be the highest order term here. And highest order term here, what is that going to be? So what's the P prime, if that is P? Yeah, so A1 plus A2x, etc. The last term being NANXN. Okay, so here my highest order term is going to be NAN x to the n times the highest order term here is going to be x squared. No, x2.
Minus one,
And minus one.
for the derivative.
Oh, yeah, sure. Yes, sorry.
So the one, this is n minus x is equal degree n.
Now, if I forget about my restriction, which was not very small, let's take any polynomial of degree n. What I want to prove is that the degree of the image is going to be n plus 1, unless n is equal to 1. This is what we get on the first examples. Okay? From that, except for this one, we get, if I plug degree 2, I get degree 3. If I plug degree 3, I get degree 4. Here, let's say I plug something of degree n. Let's see what is going to be the degree of the image in general. So we have to prove it.
But on the right side, you wrote minus an xn plus 1.
Yeah, I haven't finished. All right? What is that? I'm taking the degree of one polynomial is going to be the degree of its highest order term. Okay? So what's my highest order term here? X times an xn. Okay, so I've got an xn plus 1. Here, highest order term in P prime, as you checked, n x n minus 1. But I multiply it by some x2. Okay, so I'm going to have highest order term is going to be written as n x n plus 1. Okay, so my highest order term, so the degree of this is the same as the degree of that. Okay, unless it cancels, and the degree of that is going to be the degree of n. An x n plus 1 times n minus 1. Okay, so what do we find? If n is different from 1, this does not cancel. Okay, when n is equal to 1, this highest order term cancels. This is what we observed here. You plug something of degree 1, the x, and you get something of degree 1. Okay? Here you plug something of degree n. If n is different from 1, you will have something that is going to be written an x n plus 1 n minus 1. Okay? So conclusion of that calculation, if you plug some polynomial of degree n different from 1, you get a polynomial of degree n plus 1. Okay? So maybe I should write that. So now let's go back to the original one. Okay, do you agree with what I've written here? If we plug, if the degree of P is equal to n, then the degree of its image is going to be n plus 1, unless the degree of P was 1, and in which case the image is going to have degree 1. Okay, so what is that going to help us? It's going to help us if we want to solve for eigenvalues, eigenvectors, because we must have the same degree for the output as the input. Okay, so if P is an eigenvector for F, the only possibility is that P has degree 1. Do you get that? Why? Simply because if P is an eigenvector for F, it means that F of P is equal to some value times P. So the degree of the image of P is equal to the degree of P, because it's a constant times P itself. Okay, so now we know that if we've got an eigenvector, it must be a polynomial of degree 1. Okay? So now let's look for it. Okay? Can we find a polynomial of degree 1 that is going to satisfy this kind of thing? Okay, so what do we want to solve? We want to solve this, but for some specific p, because I have now restricted p to things that will be written like a1 plus a0 plus a1 times x. Okay, because it's a polynomial of degree 1. Okay, so let's look for that. So write the equation you want to solve on. What it means for us now, the equation we want to solve.
Excuse me.
Yep.
I don't understand why P must have a degree 1 to be an eigenvector of life.
Because we found out that the image of a degree n polynomial would be a polynomial of degree n plus 1. Okay, so that will exclude all polynomials, well, unless the degree of p is 1. Okay, so if the degree of p is different from 1, I will never be able to satisfy this equality that defines eigenvectors.
It's not a square matrix.
No.
No, not that.
No, because if you have this equality, it means that the image of p has the same degree as p. Okay, so the only kind of polynomials that have an image of the same degree of polynomials of degree 1. Any other have a higher degree for their image. Okay, so we know p must look like that. So we know that this is what we want to solve. We want to solve f of p is equal to lambda p, with p being that specific a0 plus a1x. Okay, so let's try this. So f of p should be equal to x plus 1 times x minus 3. Derivative, so that's my p a1. Minus x times p. So a0 x minus a1 x2 should be equal on the other side to lambda a0 plus a1x. Okay, so this is really what we're solving. Okay, so we just have to find, can I find A1 and A0 that are going to satisfy this? So we just have to try it. So if I expand that, we said x2 minus 2x. So A1 x2 minus A1x minus 3A1 minus A0 x minus A1 x2 is equal to lambda A0 plus lambda A1x. So as expected, the other two terms are cancelling. And we have minus 2a1 minus a0 is equal to 2 lambda a1. And I've got also, what do I get? The constant terms minus 3a1 is equal to lambda a0. So how would you solve that? Well, you've got many ways. You know that you're not going to have a unique solution because we've got to get some spans. Okay, we will get some spanning steps. So you've got many ways to do that. Either you substitute, for instance, lambda and get something related to A1, A2, A1, A0. Either you can say that what is that actually? This is really looking like a matrix equation that you're solving for the. So if I put everything on the same side, minus 2. Okay, let me put that equation first. All right, so that's minus lambda A0 minus 3 A1 is equal to 0. And on the other side, I'm solving for minus A0 minus 2 minus lambda A1 is equal to 0. So what are we looking for? We're looking for things that we can be written as minus lambda, minus 3, minus 1, minus 2 minus lambda, A1, A0, A1 equals to 0. So we are really looking for the, what does it look like when I'm solving these kind of things? Yes, this is really the matrix, some matrix minus lambda times the identity. So if I want to find non-zero values that are going to solve that, I must look for values of lambda such that this is not going to be invertible. And so then I have to make the determinant to find for which values of lambda it's not invertible. And what do I get? The characteristic equation. Okay, you solve for lambda, and then you find the eigenvectors. Okay, that's one way to solve it. Or you, so I would like just to speak a bit about the next exercise. So you can solve that, right? Look for the lambda such that this is going to give you non-zero solutions. So in the end, what you're looking for, determinant of this matrix is equal to 0. That gives you the characteristic equation. Once you have found lambda, you find the A0, A1. Well, once you have found the different values of lambda, and you should find 1 and negative 3, I think. Then you can find the corresponding eigenvectors. So I can give you the solutions. Lambda is equal to 1, lambda is equal to negative 3, and the span, the eigenspace for 1 is minus 3 plus x. And the one for the other is x plus 1. Okay, let's talk about the last one quickly. Got 5 minutes for that. Okay, last one. We've got a vector space, an endomorphism on that vector space such that we've got this relation F3 minus F2 plus f minus identity is equal to 0. What can we say about the eigenvalues of f? Okay, f belongs to L of E, some vector space. And the first question is about, assume no, nothing. It's just, what about the eigenvalues of f? So, what does it mean if I've got an eigenvalue? It means that I've got, again, eigenvector, eigenvalue, I've got something like this. What's happening if I apply twice my functions? What do we get? So, if I've got, in that case, if I've got an eigenvalue eigenvector, so f of x is equal to lambda x. Okay? So now I've got to compute f of lambda x. So what do we get? Yeah, first we use linearity, that's lambda f of x. Then we use the fact that we've got an eigenvector, so that f of x is lambda x. So, moral of the story, if you've got a linear map with some eigenvalue lambda, lambda squared is going to be the eigenvalue of the squared map. If you apply f again, you just apply f to lambda squared of x, and of course you're going to get lambda cube. Right? And so on. So, this quantity, what does it mean in terms of eigenvalues? Eigenvalues have to satisfy this equation. So eigenvalues must satisfy lambda. So, if I do that, if I apply it to x, and that so should be equal to 0, because that's the 0 map. That's f3 of x minus f2 of x, and so on. And that just gives you, according to what we've said, lambda 3 minus lambda 2 plus lambda minus 1 times x. And as we said that if I've got an eigenvector must never be equal to 0. It means that the eigenvalue has to satisfy this equation. Okay, so if I have a map that satisfies this, then it means that if it has some eigenvalues, it satisfies that equation. Obvious root to this equation. One. Okay. So when you've got an obvious root, what can you do? You factor with it. So we said 1 is an obvious root. What comes here is going to be a second order polynomial that you have to find one way or the other. And you should find that it's lambda squared plus 1. So So if we are in R, what are the eigenvalues? Just one, because this has no real roots. If we are in C, we get the complex roots, I and negative I, of these ones. Okay, so in R, the spectrum of F is just going to be 1, and in C, if my space is a space of complex items, I'm acting on complex variables, the spectrum of F is going to be 1 plus I and minus I. And is F invertible? Yes?
In R, why the spectrum is not 1 and -1?
Because -1 is not a root. I just have 1. And here, negative 1 is not a root. Okay? Quickly, is F invertible? We've got an endomorphism. We can conclude about its invertibility here. If we've got finite dimension, what do we have? We have an invertible map. So if we've got an endomorphism, okay, it's going to be an isomorphism if it's either surjective, either injective, and in any case, it's going to be bijective. Why? Because of the rank nullity theorem. In finite dimension, that's the beauty of it. If your map is linear, you only need to prove either injectivity or surjectivity. And it gives you that the whole stuff works because of the rank nullity theorem. So, if I'm in finite dimension, what do we know? We can conclude about that. What's the relation between injectivity and eigenvalues? Very important. Injectivity on a unique solution, okay? You have to be able to prove that. Unique solution means that your kernel has to be reduced to 0. Relation between kernel and eigenvalue, if the kernel is not reduced to 0, then you've got 0 eigenvalue. You've got the eigenvalue 0. Okay? We don't have eigenvalue 0 in any case, right? So if we're in finite dimension, we know that we're injective. As it's an endomorphism, we know then it's going to be also surjective, and that we have from the rank nullity theorem, and so that we've got an invertible map. Okay? So try to write correctly this reasoning, it's important. Right? And in infinite dimension, well, okay, it's the reasoning that I haven't written here that is important, but the thing is, the only justification for invertibility is that 0 does not belong, so in finite dimension, 0 does not belong to the spectrum of F in any case. So from rank nullity theorem, F is an isomorphism, an automorphism. Okay, in infinite dimension, I could have, as the rank nullity theorem doesn't work anymore, because we can't compare ranks, we can't add it to a dimension, then I can't use this argument anymore. Right? But what I can say is that this is equal to the identity, and what is the definition of an inverse? The definition of an inverse is when you apply your map to its inverse, you get the identity. Okay? So here, I can factor with F on both sides. So this relation tells me that this is the inverse. Because F times and composition in terms of linear maps is the same thing. Okay? So F applied to this thing or f times this thing is going to be the same. The identity, so yes, it's inverted. Because I can define it. Yeah?
Yeah, of course, no.
Yes, sorry, I'm going away. Right, yes, I'm sorry to keep you. Right, you have an online course or with who? Okay, I will apologize. Okay, so don't hesitate to ask me questions. I will post the midterm, not the one I did last year because we didn't have midterms because of the quarantine. But the one I did the year before, don't be afraid, it's long. And it's not exactly related to the same program. I will explain that. Because when you have identified zero, it means that you can find non-zero elements such that this is zero. Okay, that means x is kernel, but that also means that's x. Like, zero and kernel is the same thing. Okay. It depends on your map. See, for the projections and symmetries, we only have ones and zeros. But when we looked at the matrix of the one with the polynomials, we have whatever comes in the
Because we have factors.
the result. Okay. It's really the image of the map that is
It was between the exercise 1 and 2 for the both projection. Then understand why for these two the eigenvalue is 0, and in the other case it's -1.
because it's one is the projection, the other one is
Symmetry.
the symmetry.
And
Okay. If you project anything on from G, you get 0.
Yes.
That will give you the eigenvalue 0. But if you take the symmetry of anything from G, it's going to be minus itself. So you get the
Yes,
eigenvalue
because
1.
here it's G on F.
Yes,
But
along G on F, and here it's along G, but with respect to F. You get on the other side of it.
so it's not the same.
No.
Okay.
One is the symmetry, the other projection.
Okay. So the symmetry around the point.
We haven't done that.
And you know,
Okay.
continue
But
on-
yeah, but that's we will do that, but it's
But it's
easy.
not it's not 1 and -1. In
It's
this
going to
case.
be minus everything.
And do you have the copy from the midterm here?
That's what I said. Not last year because we didn't have any midterms because of the deadline, but the year before, yeah.
No, the copies of the last midterm.
Oh yes, in my office.
So,
Sure.
where is your office?
The same as Mr. Odren. First floor here,
Okay, first floor.
in front of the space.
So here, the one we just did, it's not inverted.
Yes, it is.
But the kernel is not only 0.
We don't have any. Yeah, it is because we don't have eigenvalue 0. We don't have eigenvalue 0 in that finite dimension. We don't have eigenvalue 0, so I know that the kernel is reduced to 0. Think about this later. Okay?
Okay. If you post it, I will watch it again.
Okay.